Okay, so I just want to talk about the multidisciplinary future of geodesy as I see it. And you could completely ignore everything I'm saying and just, go work at Google and make a ton of money, linking cats to mental illness or whatever. But integrated studies using multiple instruments and co-located instrumentation will be crucial. Anthropogenic interactions with the Earth's surface. Moreover, looking at climate change and how that interacts with the solid Earth. And also linking different Earth systems such as biology, chemistry, and ecology. So I wanted to start off with something really strange here. This is a very long time scale sort of study, but it gets at the fact that our solid Earth actually has an impact on genomic diversity. And as we go towards smaller scale, sort of high strain rate environments, we can start to look at how gene flow works, and we can really start to get ingrained into ecology. Now, for the next few slides, I'm just going to talk about seismogeodesy using high-rate GPS in a seismological sense. This is one of the first studies doing this. This is actually looking at teleseismic waves from the Denali earthquake, and it's crucial in that it's changed the way we've looked at how this data is in our environment. We just expect to have high-rate GPS data coming in. Now, going a little bit further, combining seismic and GPS data, as others have alluded to, we can really start to get down to a true seismic level. In this case, this co-location allows you to reproduce broadband velocities that completely match broadband seismometers in the near field and don't clip, which is huge in the future of strong motion seismology. Moving on to something a little different for borehole strain meters. It's a huge part of PBO. Very few people know how to use it. There's Duncan, and that's about it. But here, using a very simple scaling relationship, we can actually determine the size of an earthquake based on uncalibrated borehole strain measurements, based on just its simple distance from an earthquake. And it will be really key in terms of including this data into Cascadia and other regions where the instruments already exist. Now, getting onto that multi-instrumentation part of things, this study is looking at how inversions change based on looking at different types of data and where their resolution is best. And really the key point is more data is almost always better. It is always better. I don't want to downplay anything. There's definitely bad data here. So moving on to climatic issues, Adrian published this paper. Bill Hammond has also done a very similar study. I'm sorry, Bill, I can't include your paper. But in this case, ongoing drought conditions cause uplift in the western United States. And this is very key in terms of linking. Geodesy has a really crucial role here in linking climate change globally and also in the US. Now, going into that other realm of anthropogenic, or if you want to call it anthropogenic for climate change, subsidence can actually be linked to carbon loss in drained peatlands, which is something you don't really think about, that geodesy has a role to play here in really the global carbon cycle. And we don't really think about that much, but it's definitely there. Now, to move on to my realm, in my backyard, we have this the largest tunnel boring machine in the world. And it got stuck, and they had to dig a hole. And because of that, they had to pump out a bunch of water, and that's causing a ton of subsidence in the Pioneer Square neighborhood of Seattle. And we have a huge impact on our near field solid Earth, and geodesy definitely plays a role here. And I'm just going to finish by throwing up PBO H2O. Everything, the whole idea of everything I'm talking about has already been done by Christine Larson. So, the future geodesists can blame her if they can't, get a job. All right, thanks.